Hello everyone, Mr. Fawcett here, and we are back for part 2 of our first geometry lesson dealing with points, lines, segments, and planes. In the first part of this lesson, we just went over the definitions and we talked about the important parts of each one. Today we're going to focus on some questions that really make us think a little bit harder about these definitions and make sure we know the differences between the different ones. So we're going to go down to the third page. As always, I encourage you to do these problems on your own first and then come back and look at the answers and explanations. So number one, for actually all of the first three problems, we need to say what the figure is, so the type of figure. Is it a point, line, plane, segment, ray? Then we need to name it using correct notation. And then we need to do a little explanation. So we need to say, I know this is a blank because, and then we need to write a little explanation. So I'm going to pause the video myself, put the answers up here, and then we're just going to talk through them. All right, so we have a segment here. We would name it as segment PQ. Make sure you do not put arrows on this bar right here, otherwise it would be a line. You of course could switch up the letters and call it QP. I know that QP is a segment because it is part of a line with two clear endpoints, and that just goes back to the definition. Number two, so we have a plane. We can call this plane R because that is the letter that is not a specific point on the plane. Or we could say plane AJX because those are three non-collinear points on the plane. And I know that R is a plane because it is a two-dimensional surface that extends infinitely in all directions. So it has an infinite length and width, but it has no depth. Okay, so it is not three-dimensional, it just has an infinite length and width. All right, let's move on to number three. All right, so we have a line. We can call this line GH or line HG. Make sure you have the bars on the line symbol above HG. And I know that HG is a line because it is a one-dimensional figure that extends infinitely in both directions. So again, just one-dimensional. We can only look at its length. It has no width. It has no depth. And it extends infinitely in both of those directions. Okay, let's look at numbers 7 and 8. So we're using the image below to answer questions 7 through 10. First question is, are points E, F, and C collinear or non-collinear? And I just realized I gave you a yes or no question. That's not accurate. So we're just going to circle the correct one. E, F, and C, let's just highlight those. E is the intersection here of those two lines, F and C. So they do all lie on the same line. So yes, they are collinear. And it says if they are collinear, name the line on which they lie using correct notation. So we can choose any of those points. We just can't choose all three. We need to choose two out of the three. So a couple options are, we could say line, that is very poor. Let's do that again. Line EC, we could say line CF, we could say line FC, and those aren't the only options, but you get the idea. Just don't use three letters, use two. We could actually do one more. Let me put that up there. It's also called line M, so we could say line M. Because M is not a point on the line, it is strictly just the name of the line. Next question is, are points C, D, and P collinear or non-collinear? So let's erase those and highlight the other three. C, D, and P. C, D, and P. So they are non-collinear. You cannot draw a line between all of them. And if they're non-collinear, we need to change one of the points in the list to make them all collinear. So really the only option we have here is to change C to E. So if we get rid of C and we change C to E, we now have 3 collinear points. So change C to E. They ask another question, what is another way to name line M? Well, we did that up above, right? Pick any 2 points on the line. I'm just going to choose, haven't used FE yet, so we'll just say FE. Okay, number 10, which of the following answer choices name the line shown that contains point P? Circle all of the possible answers. So let me erase this. Line L. Does line L contain point P? It sure does if I drew that a bit better. I think you can see it without, yep, there we go. So that's good. Line PD certainly contains point P because P's in the name. FP has to contain it. It's in the name. Oh, you know what? Let's go back. It does say, so FP would be a line that contains P, but I did word the question in a way that says name the line shown. So FP, while it is a line, because we can draw a line through those 2 points, it's not an actual line in the diagram. So we could skip that. I would not write a test question where I think this is a little ambiguous. You could make an argument that FP is a line, but it does have this clarifier in here that says it needs to be shown. So I would say technically we should not circle that. Line DE. So if we draw line DE, that line does contain point P. Line EP, or points E and P also lie in that pink line, which is drawn. So we will circle that. And line PC, this is another case where PC could be a line because any 2 points form a line. However, it's not one that's drawn in our diagram, right? We'd have to sketch this in ourselves. So this one would not be correct. So we do have these 4 choices that I circled. Those would be the correct answers. All right, let's move on to the last page. Quite a few questions here, but they are pretty short. If you understand your definitions, these aren't too terribly difficult. Question 11 says, what is another way you can name plane V? Well, again, naming a plane just requires that we name it using 3 non-collinear points. So I could say plane, pick 3 non-collinear points. Let's go with Z, R, and Q. Not our only options, but certainly 3 that are non-collinear. Then it says name line S in another way using correct notation. So line S is our line right here. This time we just need to pick 2 points on the line, exactly 2, not 3, not 1. I'm going to go with RX. Okay, question 14. Where do lines GH and BA intersect? So if we draw these lines, I'll do GH in pink, right, AB in blue, and they intersect right at point D. So to answer these questions, 2 lines always intersect at a point. There is a case where lines never intersect, right? If you think back to Algebra 1, that would be parallel lines. But if they do intersect, then they're always going to intersect at a point. In this case, it's point D. A quick segue, or it's more so of a rabbit trail, But there are three options for when you have lines, right? You can have lines that are parallel and they never intersect. You can have lines that intersect once, or sometimes you may have lines that end up being the same line. And in that case, we don't say that they intersect an infinite number of times, we just say that they are the same line. So if lines intersect, they will always intersect at exactly one point. All right, let's look at 15. It says, where do planes FDG and ABCD intersect? Well, if we look at these planes, the intersection point is this line right here. Now I know it looks like a segment because it looks like A and B are endpoints, but we have to remember that these planes extend forever. Oops, had my eraser instead of my pen. We do have to remember that these planes continue to keep on going. We just can't draw an infinite plane on a sheet of paper, right? Because we need an infinite amount of paper to draw an infinite plane. So you just have to kind of visualize in your head that you would extend those flat surfaces indefinitely, which means that their intersection would be a line, not a segment. So two planes intersect, and I almost just wrote the word segment because I had been saying that. They intersected a line. In this case, it is line, we'll call it AB. You could, of course, call it DB, AD, BA, etc. Now, just like with lines, planes could also have the same possibilities. Let me scroll down here so I give you guys a little bit more space to see. Don't have too much, but we have some. I will do it right here. So we have three options. We have a possibility where the planes are parallel. In that case, they're never going to intersect. So that would be when they are essentially on top of one another. You could think of if you held two books parallel to one another, like one book above the other one, and you thought of those as planes. If you extended them in both directions, right? If I extend these planes in both directions, they are never going to intersect. Our other option is the planes intersect, which is what we see over here. So they intersect at a line. And the third option would be if the planes were the same plane. So if the planes were directly on top of one another, we wouldn't say the planes intersect in infinite lines. We would just say that they are the same plane. But if the planes do intersect, the key thing to note is that they will intersect at a line. Okay, let's look at the last three questions, and then we are out of here for video 2. It says, determine whether each statement is always, sometimes, or never true. Write the correct word in the blank. I love these types of questions because they really make you think through many different examples. Okay, you may find a time where this example does work, but then you've got to think, okay, does it always work, or is it just in this specific case? You may find a time where an example doesn't work, but then you're like, okay, does it never work, or does it sometimes work? So I like these questions because they make you think. So the first question is, a segment blank extends with no end. So you could just read this with each of those words. We could say a segment always extends with no end. Well, we know a segment has to end, right? We know a segment has two clear endpoints. So it can't extend with no end. So it can't always extend. It can't sometimes extend. It never extends with no end because it has two clear endpoints. Number 18. I'm not sure why I skipped 17. Collinear points blank lie on the same line. Collinear points always lie in the same line. Collinear points never lie in the same line. Or collinear points sometimes lie in the same line. Well, by definition, collinear points have to lie on the same line. So they always lie on the same line. If the points were not on the same line, right, we would call these non-collinear points. The only way that they're collinear is if they all lie on a single line. Last question, line TQ and QR are blank the same line. Are they always the same line? Sometimes the same line? Or can they never be the same line? Here's where it may help to sketch some examples. So, could you draw an example where they don't lie on, where they're not the same line? So, let's say here's T, here's Q, and let's say here is R. So the way I drew it here, right, we have two separate lines, one for QR. All right, so my software quit out on me, so it may look a little jumpy in the video, but I had to go back and redo this. The first example I drew, we can clearly see that lines QR and QT or TQ are not on the same line. So we know that this answer right here can never be always because we just came up with a counterexample. Now, we're between sometimes and never. So if we can come up with an example that's true, then we know that this is sometimes true. If we can't find an example, then we're probably going to go with never because we can't find an example for when it is true. So you should try this on your own. Can you draw a scenario where these end up being the same line? Well, they end up being the same line if all the points are collinear. So T, Q, and R. This way, QR is going to be the same line as TQ. Okay, and if they're collinear, those lines will include all 3 points. So this answer is sometimes. Sometimes it's true, sometimes it's not. It depends how the diagram is drawn. Okay, that's the end of our first actual geometry lesson. I look forward to seeing you next time. Until then, though, enjoy the rest of your day.